My name is Uriel. Thanks all for coming, and thanks Uri for inviting me. I'm honored to be speaking here at PyData after several meetups in which I was in the attendance and not in this side of the stage. A bit about me, as probably my accent already sold me, I'm from Argentina. I lived several years in Uruguay. I know that here there is some Uruguayan people, so I had to say that. And 8 years ago, I came to Israel. I studied in the Hebrew University of Jerusalem, then in Tel Aviv University. Yeah, everyone's happy. I also did one course in the Technion, so. And now I work as a data scientist in Rainforest. I will tell later a bit about Rainforest. But during my work there, I got exposed to a type of models in machine learning, which are probably not very popular, but are really useful and with a lot of applications that they are called learning to rank. So just to be sure, who's here work frequently with learning to rank models? Okay, there are a few. How many of you heard about learning to rank? Okay, a few more. That's great. But yeah, before I started working in Rainforest, I've never heard about learning to rank. So this was very interesting for me, and I want to share with you some of the things that I learned in the last year. Okay, so first of all, what is learning to rank? Very simple. It's the usage of machine learning to build ranking systems. And where can we find them? Well, in search engines. That's probably the most famous application of learning to rank. Also in e-commerce websites, hotels search engines, and streaming services. There are some more applications, but probably those are the most famous ones. And all of them use some form of learning to rank. Sorry. So what's the use case in Rainforest? Rainforest is a company that tries to empower consumers by simplifying their research and giving them the possibility to make more informed shopping decisions. How do we do that? We have some websites that show the best deals available and do some product comparison, and we get our product database from several retailers online. Also the largest one, but also some small retailers. Why learning to rank for us is important? Because obviously when we are doing both, like when we are showing deals or when we are doing product comparison, in everything that we show to the user, we want to show them the most relevant or better products on the top of the website, and the less relevant, we want to put them on the bottom or not show them at all. And the first question is, why is it different from regular classification or regression in machine learning? That's a question I made to myself. Why is it different? And it's actually not very different. If we think of, for example, the problem of just classifying a relevant item from a not relevant item, I could be using a classification algorithm. And if I'm just ordering things according to some ordinal score, for example, ratings from 1 to 5 or ratings from 0 to 10, those are the typical numbers, then I could use regression to predict this score and then order products or items, in our case it's products, by this score. And this is called pointwise learning to rank. But what if instead of doing that, we can actually, for the same query, we can compare during the training the different products that we have available. And we can do it this pairwise, so we will take each pair of items, documents, or products and compare against each other and decide which one is the best one. And The second option is just take the full list and try to do some optimization about it. So we could use regression and classification for learning to rank problems, but that's not the optimal way to do it. And the comparison during training of different documents, it's what actually makes it different. And then now that we know what is different and what is the meaning of doing learning to rank, the first thing that we can ask to ourselves is, okay, I will train a model, and based on what I'm going to optimize it. And those are some of the most common metrics. But I will focus only on NDCG, normalized discounted cumulative gain, because that's the metric that we use at Round Forest. So what is this metric? It's a sort of a relevance score for the full list. So what we see here is that first we can, for every ranking that we have, we can compute the DCG, discounted cumulative gain, which is basically the sum of the relevance scores of all the items until some position P. And they are weighted by the position in which they are shown, because usually we are most interested in the first positions than in the last ones. So we make some discount over the positions. And finally, we compare this to the ideal DCG, and we get our metric. One of the good things about doing this is that it's very simple to transition from a regular classification or regression problem to learning to rank. And in our case, we use the boosting algorithms, and all of the main libraries for boosting have the possibility to work with lambda rank, which is a way of optimizing ranking systems. In our case, now we are using a light GVM, and it's very simple to do it. We just have to say that the objective is lambda rank. We have to say that the metric that we are optimizing is NDCG, the position in which we are optimizing it, that in our case it's the position number 10, so we are only taking into account for the optimization the first 10 items. And the last thing is that we have to sort our input according to the query ID. So in our data set, we have products that correspond to a particular user query, and we order them by their query, and we say to the algorithm that which are the lengths of each query. So if in my G train, which relates to the group, I will have in the first position, let's say 5, that will mean that the first 5 products correspond to the first query. We have a set of features. We want from those features to get an output. And if I see this as my X and Y, the first question, another question is which is my Y and where can I get it from? And essentially I have 2 possibilities. The first one is get some explicit feedback. That will mean that I will have some judges, probably I will hire them to go over a few queries, not a few, actually a lot, and say what is relevant, what is not, or give a score. But this usually it's very expensive. I cannot get a very big data set, and I cannot always trust the judges, and they also don't represent the common user, because the judges that I'm hiring, they are not necessarily think like the users that actually come to my website. So the alternative is to have some implicit feedback. That will mean that I will use the engagement of real users as a metric of relevance, and using this I can get a lot of data. It represents well the average user that comes to my site. But the bad side is that usually this data, maybe it's not of a higher quality, it's a bit ambiguous, it's noisy, and as we will discuss now, it's also biased. So what are the challenges here? The first one is position bias. This bias, it's usually very natural. When I show the user the different items in a query, I'm showing him these results by a certain ranking or a certain order, and this order affects the engagement. And after I have this engagement, I'm going to use this in the training data, and here we have the bias. So how can we solve or at least reduce the bias here? The first one is just use random samples. Instead of using samples based on some ranking that I did in the past, I'm just showing for a small percentage of users completely random results and using this for training purposes. The problem is that if I have a brand that I want to expand over the time, even having 1% of the users having random results, it's very bad for the business. The second one is that I can do it filter unseen results. Unseen, I mean things that I'm not sure that the user has examined. So I'm only considering, for example, if I have a problem in which I'm looking at what was clicked and what was not, I will probably take things that are above the last click. And the research paper that I mentioned here suggests that we can do that we can estimate the actual position bias by using a expectation maximization algorithm. And the good thing is that we can also use the same feature set of our learning to rank model. And then after I estimated the bias of the position, I can use the inverse of it as sample weights. So this way, for example, the clicks that I'm getting in lower positions will get a stronger weight than clicks that I get in the first positions. And the last option, or at least options that we use in Randforest, it's something suggested by Google's rules of machine learning that says that we can use the position as a feature of the model, and then when we are in production, we can use the same constant position to predict, or leave it as NA. But this has a small problem that sometimes it's not consistent. The ranking that I get by predicting everything on position 1, sometimes it's not the same that when I leave it as NA. A second challenge that we have in learning to rank is context awareness. If I use features that are only dependent on the document, for example, in Randforest we have the price of a product. If I use only the price as a feature, then I'm not sure. Okay, I have this price that could be $40, but it's $40 when all the products are around the $100, or this is $40 when all the products are around $40 or $45. That changes a lot, and the first recommendation is to use also features that are relative to all the other documents in the query. And the second suggestion also by a research paper that says that we can, of course, use deep learning, because nowadays we have to use deep learning for something. We can create the context by some representation of a neural net. The two possibilities that they suggest is first evaluating each product against each other and aggregate the results on a matrix, and then use a convolutional neural network to transition from this matrix to final scores. And the second solution that they say is that we can first aggregate all the products in in a context vector. It will be a sort of embedding, and then use this embedding as extra features for the model, and then get these scores. And the last challenge is lack of diversity. I think this is the main problem of learning to rank algorithms. It's that learning to rank algorithms are built to score the items according to their relevancy. But for example, if the user is searching, I don't know, best mobile phones, and the most relevant result could be iPhone X, right? And the second one could be iPhone 9, and the third one could be iPhone 8, because they are one of the best mobile phones, and it's logical that that's the model will say. But the user don't want to see. If he's generally searching mobile phones, he doesn't want to see all iPhones. So we also have to solve this problem. How can we solve it? We can create a similarity matrix of the different documents that we have, and use the elements of this matrix as a regularization parameters to penalize similar items in close results. The second one is to do some sort of re-ranking. First, we rank, like we use the original ranking, we rank according to relevance, and then we try to do a new ranking that tries to optimize diversity, subject to that the original ranking is not affected too much. And the third solution, which is what I prefer, it's doing some greedy optimization. I have my original ranking, and I only add items that do not decrease the general diversity of the full list. So I think that I spoke a bit too fast, but I'm done. So questions?
We talked about NTGC, which is a metric to evaluate the ranking, but what about some kind of loss functions that are optimizing ranking? Because from what I know and what I see in researchers, when they evaluate ImageNet models and stuff like that, they do use some kind of ranking because they measure the top 5 accuracy, the top 10 accuracy, but the model wasn't really trained to rank, just based on the submax overall of the data. So how do you actually train a network to learn to rank?
Okay, so first of all, I'm not an expert on this side of the optimization. I'm more of a data person, but as far as I'm concerned, the usual methods take each pair of items that I have on the same query, and it's a sort of classification in which I say, is this item better than the second one? So they transform the observations to pair of observations and do some sort of classification. And the difference with the lambda rank is that they don't need the actual classification, but they only need the gradients of this classification. But I'm not an expert. That's what I think. Yes.
So, following this question, so what you train it on, if it's implicit data, so you take only the positive versus the negative, or also inside the positive you make some ranks, because either can work.
So suppose that I'm now classifying I'm classifying a particular pair of items, and there are two possibilities. One is better than the other one, right? Or they are the same, according to my score. So basically, that's I'm just classifying, is item 1 better than item 2? Is item 2 better than item 1? Or they are the same? That's the answer.
But you're using implicit data?
Yeah, that question, it doesn't matter if it's implicit or explicit. Implicit means that, for example, I could use if a user clicked or not on a product, if the user ordered a product or not. So in our case, for example, we use 0 says that the product wasn't clicked, 1 means that the product was clicked, and 2 means that the product was ordered. So So 2 bits 1, 1 bits 0, and we do the classification based on that.
But you don't do it inside the 2, inside the 1.
Oh, okay. So she's asking how do I deal with 2 different users that for the same query ranked things differently. One clicked on something and the other clicked on something else. And this usually it's embedded in the context. The context, not in all cases, but in most cases, explains well which user I'm dealing with. So I have features that represent also the user. For example, I don't know, demographics or technological details that I have on the user. Okay, thank you very much.